Hello everyone, welcome to today's video where we're going to delve into biostats for USMLEs, either step 1, step 2, step 3, step 4, 5, there is no step 4 and 5. So the whole idea of this video is to cover, I would say, about 20%, or if I want to be more accurate, maybe 15 to 20% of the types of questions you see in biostats. It's obviously not going to cover the whole thing, but it will cover things that show up on the exams. They show up, they are important, they are very concrete. They are very important, very oftenly tested, it's undisputed. So we will get started, and the whole version of the whole biostats, I'm going to put it on my website and announce it on social media. The links to the social media are going to be in the description. However, this video is going to cover a good proportion of biostats, and I hope that really helps everyone improve their understanding. Because what I believe is a big issue, that people try to memorize it, similar to the way they memorize the algorithm for pulmonary embolism, or say, blunt abdominal trauma. However, biostats is best solved when you understand it. If you do understand it, you will solve it. So that's my aim today, to make you understand and also solve. Usually, I let the one that I'm teaching, when I'm tutoring, go through the questions, and then I see their pattern of thinking, I explain to them why it's C instead of B, and explain the topic as a whole. However, this video I'm alone, so I will be joined by my beautiful cup of coffee, which I will take a sip of every 5 minutes, if you allow me, and you as a watcher. So I will solve the questions, but first I will explain the topic so you understand the rationale when I'm choosing the answers. So let's get started. So the first topic is about normal distribution. This is the normal distribution. It has the famous pill-shaped curve. Basically, the whole idea of the normal distribution is that people are distributed in an equal way, where if you have the middle value, so let's say we are talking about an exam score. Someone could score 0 because they solved all of the questions incorrectly, they will be down here. And someone would score 100 because they are nerds and they solved every single question correctly. So that's your spectrum. Now in real life, probably it will not be normal distributed. You will not find many people scoring 0 and 10 and 20. Even people who fail, they will be in the 40s, 30s range. However, if you assume that the scores of the class take a normal distribution, this means that the most common score in the class is 50 because it's in the middle and it will be here. It's the mean, so if you combine all people's scores and divide it by the number of students in the class, you will get 50. It's the median as well, and that's a feature of the normal distribution. The mean equals the median. So if you put all the scores on a paper, and you organize them descendingly, ascendingly, the value in the middle is going to be 50. And it's also the mode. So if you ask someone what's the most frequent score you have heard of in the class, it's 50. So the mean, median, and mode are equal, and that's a feature of the normal distribution. So all of these values stack here in the middle, mean, median, and mode. And 50% of the class students scored higher than the median, mean, mode. 50% scored less. So that's how the plot is interpreted. Now, another feature of the normal distribution is that we have our standard deviations. And a standard deviation could be calculated using data. I'm not going to dig there because it's more of a mathematical thing, and in USMLEs they don't let you calculate the standard deviation, or mean even. So the standard deviation basically describes how far I am from the mean, specifically the mean. It has nothing to do with the median and mode. Here it happens that they are equal. So how far am I from the mean? So let's say that the mean was 50, and let's say that the standard deviation was 15, all right? So what this plot is trying to say, this is 0 standard deviation. this value here has 0 standard deviation. What does that mean? That means its value is exactly the mean. Because whenever I'm calculating any single value, it's going to be x multiplied by standard deviation plus the mean. And this will tell me how far it is from the from the mean, and will allow me to calculate it. So standard deviation is how you deviate from the mean. So if it's 0, if it's like I'm not deviating, I'm not like there is standard deviation, it's one value for the class, it's 15. However, I happen to be someone with the most frequent score, so I'm not deviating. However, if someone deviates by 1 point to this side, meaning that they gained 15 points on the exam, one standard deviation, they will score 65. If someone is 15 points less than the mean, meaning -1 standard deviation, they will be 35, because 50 minus 15. Now the feature here is that I'm building up to between -1 standard deviation and +1 standard deviation, you have 68% of the responses. So you can confidently say in your class of normally distributed scores where the mean is 50 and the standard deviation is 15, that 68% of students score between 35 and 65, meaning 50 plus minus 15. So plus 15, which is the standard deviation, 1 time, it's here. Standard deviation 1 time, but on the other side, so minus, it's here. So 68%, and as you see from the numbers here, 68 is basically 34 plus 34. So we can also say between 50 and 65, so the mean plus 1 standard deviation, 34% of people in our class exist. And between 0 and -1 standard deviation, so 50 minus 15, that's 35, 34% of the class does exist. And again, if you take it from 35 to 65, it makes sense, you will combine these two numbers, so 68% of people exist. Now if you take it further, instead of using 1 standard deviation, you use 2, meaning you will add 15 twice, we will go to this point. So between 2 standard deviations, plus and minus, it's from this number till this number. So you add 30 to 50, that's 80, and here it's 20. So between 20 and 80, you have how much? 13.5 plus 34 plus 34 plus 13.5, that's 95%. So 95% of the responses are within 50 plus minus 30. Because again, it's 2 units of the standard deviation, and the standard deviation is 15 in our example. So you can confidently say, if they ask you, within what range 95% of the class scored, you say between 20 and 80, under the assumption that our scores follow a normal distribution. Lastly, if you take it up to 3 standard deviations, you are almost hitting 100 or 99.7. So depending on the plot, some plots will make it 99.7, some will make it 100. That's fine. It's not a territory that you will be asked about. Usually they ask about the second and the first. So how do they ask? A researcher is creating a normogram. This is a normogram. So it's a plot of a normally distributed data of the heights of patients with genetic short stature due to this mutation. The heights are normally distributed, and the standard deviation is found to be 29. If the mean is 145, what range of heights would include 68% of patients? So knowing, because you have memorized it and you just understood it, that 68% basically says mean plus minus a standard deviation. That's the range where 68% of people exist. So you will take your mean, add standard deviation to it, that's going to be your upper limit, and take your mean minus your standard deviation, that will be your lower limit, and the answer will end up being B, because 145 plus 29 is 174, and 145 minus 29 is 116. So that's how you answer this question. I hope you got it right. If that would have been replaced by 95%, let's say this is 30 to make it easier to our calculation, then I'm adding 60 because I'm adding 2 units of the standard deviation, so it will become 205, it will be 203 because we added 2. And if I'm looking at the lower limit, it might reach 80 or something like that. It will be in that range. So maybe I didn't calculate it very thoroughly, but maybe it will end up being this number. All right? And if you're looking into 3 standard deviations, it might be this one. So as you can see, we are getting a sense of it. So that's how you calculate it, and there is other applications for it in confidence interval where we use the 95%, but that's not going to be covered today. I will try to focus on other topics while we move on. Now, another question based on the normal distribution, that's a tricky one, is this one. So a clinical trial has demonstrated that a new medication is effective in reducing diabetes risk in children aged 18 with a BMI greater than 95th centile. So if your BMI is more than 95th, not 95th, more. It's not more, greater or equal, it's greater. So if you are 95th, the medication doesn't work for you. You have to be more than that. The BMI distribution of the population is normally distributed with a mean of 50. Wow. Amazing. Imagine a BMI of 50 being the mean. And the standard deviation is 15. So it's similar to the example we were breaking down with the scores of the class. And they ask if a patient is eligible for this medication given that their BMI is 80. So basically a clinical trial said if your BMI is more than 95th centile of the population, actually to make it easier, I'm changing it to 96th. How about that? That will make it easier for everyone to avoid any confusion. So if your BMI is more than the 96th, then you are eligible for the treatment. So 95 is completely ineligible. And this guy came to my clinic, he read the study, and he says, I want this medication. His BMI is 80. So we need to figure out if it will work with it for him. Is he more than 95th or 96th now or not? How will we know that? Well, let's see. We will go back to the normal distribution. Now we are no longer talking about ranges. So when we were answering this question, we said this is the range where 68% of people exist. That's a range, all right? While now what we are trying to calculate is an individual centile, like where do I stand? Am I the first on the class? Am I the last? Am I in the middle? All right? So if you look here, 0 is 50, as we said. 1 is going to be 65, and 2 is 80. And our gentleman's BMI is 80. So he's here. So is he more than 96? The trick here is that, again, you will think of ranges. You will remember that when we were pointing here, we said that between this point and this point, 95% of people exist. And that's your mistake. Then you will think he is number 95. So he is not included, and the medication will not work for him. And you will answer no. However, this is incorrect. Again, the concept we discussed initially is ranges. So between 2 and minus 2 standard deviations from the mean, 95% of people exist. However, that doesn't mean this guy is guy number 95%. It doesn't mean that, because if you look here, from here to here, we said it's 95. So from here to here, it's 95. And then you have 2.5 here. So if we look like from 0 up to him, he's actually 97.5. Because there is this 95, and then there is this 2.5. So he is 97th centile or 97.5 centile, meaning he is more than 95, more than 96, and he is eligible for this medication. However, if you looked at the range and you were tricked to think that this point is the 95th centile, then you will answer incorrectly. So that's the trick from this question. The correct answer is D. I hope we got it right together. Obviously, in this video, feel free to pause and try solving on your own. I will drink a sip of my coffee. Good coffee. All right. So I'm going to just show you here what I meant. So I have my pen. So I'm standing here. That's my BMI. Okay. From my point till my thin brother's point, that's 95% of people. However, that doesn't mean that I am the 95th centile. If we are 100 in the class, there is only 5 people that are heavier than me. It doesn't mean that. Why? Because again, look at the range. We start from here with 0, and that's like the highest weight. So there is still 2.5 here. So when you calculate my centile, basically when you say I'm 95th, if we are 100, I'm the 95 heaviest individual here. Only 5 people are heavier than me. So I'm heavier than these people. Why they are not included? Again, that was discussion of a range. Here it's a centile, so you will include them. So everything below me is this. So 95 plus 2.5, I will end up being 97.5. Similarly, if we look at this point here, when we said 68%, it was between him and between this gentleman. When we said 34, it's between him and between this gentleman. However, when you calculate his individual centile, it will be this range. So it will be, we know that this is 50, so it will be 84. So he is at the 84th centile. And if you add 13.5 to 84th, what do you get? 97.5. So I hope you get the point, because I'm moving on from normal distribution. Please comment out if you didn't get it. I will try to simplify it further. Okay. Now, a large study, I'm going to explain the topic first. So, hypothesis testing, that's the second topic of today's video. Hypothesis testing, whenever we do a research, we are trying to claim that there is a relationship between 2 variables. Let me say that again. Whenever we do a research project, we are trying to claim that there is a relationship between 2 things. It might be smoking and Crohn's disease, smoking and lung cancer, alcohol and cirrhosis, nitrosamines exposure and gastric cancer. You think of it. Being a medical student and depression. So all of these are hypotheses that we try to test. Now, when we test these hypotheses, we utilize statistical tests like chi-square, one-way ANOVA, t-test, and these are important for USMLEs, not covered in today's video. However, the topic I'm covering is really very important and is the basis for many questions about these statistical tests. Every statistical test, everyone, all of them, are going to return you 2 things: an effect size, which I'm not covering in this video, and the p-value. And the p-value is the one I'm covering now, along with the explanation and the interpretation of your findings. So I hope you understand what I'm going to tell you and I'm going to cover. So let's start from the interpretation of the findings. Now let's say, which is stupid of me, but I'm thinking of studying the relationship between obesity and diabetes. Give me Nobel Prize. Does obesity cause type 2 DM? So this is a question that have been answered extensively. Most 4-year-olds probably hear about it nowadays. So it's a true hypothesis. Before me trying to experiment and know if it will be true or not in my sample, because I will not sample every human on earth. I'm going to grab 100 individuals from the community, from the clinics, measure their weight and their blood sugar, and determine if there is a relationship. So maybe in my sample it will be biased, I will cheat, and I will say there is no relationship. However, this will not defy the solid evidence supporting that there is a relationship, which is now in concrete, it's in ground. So we know that in life it's true, obesity and diabetes are related. So I'm stupid enough to do this research idea, bear with me. So when you do your research idea, like my claim that obesity causes diabetes, I'm trying to rediscover the wheel. When I say obesity is associated with diabetes, this is my H1. It's the alternative hypothesis. So in every research question, there is 2 hypotheses. There is an alternative, which is the presence of an association, saying that obesity increases the risk of smoking, saying that smoking increases the risk of Crohn's disease, saying that smoking protects against ulcerative colitis. So even if the association is positive, like saying that Ozempic reduces the risk of fatty liver disease, or now they call it metabolism-associated liver steatohepatitis. So whatever it is, regardless of the direction, just saying that there is an association, whether it's a positive in its impact or negative in its impact, this is an alternative hypothesis that you are trying to prove. The opposite is the null hypothesis, which is also incorporated within your research question, which says there is no association. And again, it says no association. It doesn't say the opposite direction. So if my alternative hypothesis I'm claiming while trying to rediscover the wheel that obesity increases the risk of diabetes, the null hypothesis will say there is no relationship. It will not say obesity protects. All right? So I hope you understand the statements of the alternative and the null hypothesis. Now again, the example we are breaking down is proven to be true. The alternative hypothesis, which is symbolized as H1, is proven to be true. We know in real life that obesity increases the risk of diabetes. So H1 in real life is true. And H0, which is the null hypothesis, is false in that example. Now, put my idea on the side. There is 4 possibilities whenever you try to do a research question. It's either you will say in your experiment that H1 is true, meaning the alternative hypothesis is accepted, meaning obesity increases the risk of diabetes. So the association you were looking for is there. And in real life, it is there. So H1 meets H1. Or you say there's an association. However, in real life, the null hypothesis is the true one. There is no association. So there is an error here, where your data did not predict reality. And it didn't meet reality. Maybe you will meet reality. You will say that there is no association. And in real life, there is no association. Or maybe you will commit a different type of error, where in real life, obesity increases the risk of diabetes, but in your sample size, it didn't. And that will be here. So in real life, the alternative is true, H1. And in your experiment, the null turned out to be truth. So these are the only 4 possibilities. Either both reality and me say H1 is true, there is an association. Either both me and reality say there is no association, so H0 meets H0, or null meets null, or there is a conflict, where we say different things. And whenever there is a conflict, it's an error. And there is 2 types of errors. Type 1 error is going to be named false positive, because you will say that there is an association, however, that is false, because in real life, the null hypothesis is true. That's like saying that obesity increases the risk of glioblastoma multiforme, some high-grade CNS tumor, and there is no proof in the literature and in real life that it increases that risk. So now you are claiming, and you found in your sample, that this alternative hypothesis is true. However, based on accumulative evidence, it's not. So you said it's true, it's not. You are a type 1 error, false positive, and that's represented by alpha, which I will talk about in a bit. The other type of error, the example of obesity and diabetes. Literature confirms that obesity raises the risk of diabetes. Then I come and claim from my data that it doesn't. So the true hypothesis is the alternative, there is an association. I claim that the null is true, that there is no association. And that's a type 2 error, false negative, beta. So I want you to remember this because it will solve you some questions. Type 1 error, false positive, alpha. Type 2 error, false negative, beta. Why false negative? I said it's negative, there is no association. However, it's false. There is an association, all right? So that's the explanation of this table. Now, the most important thing to get out of this table is alpha. Beside the naming, knowing that's a false negative is type 2 and the false positive is type 1, and understanding what H0 and H1 mean, the null and the alternative, you need to understand alpha and how it relates to p-value. And that's what I will explain now, and it will help us solve the questions. All right? You can pause the video, replay the parts that I have been talking about. Usually I walk through one question and another. However, I feel that's better when I'm interacting with one individual. While when I'm trying to film it, it will be really easier to explain the topic as a whole and then go through the questions. So it's your duty now to replay parts. If you didn't understand it, comment out. I'm going to help you. All right? So alpha is the chance of committing a type 1 error. And alpha is predetermined. It's a cutoff. So you will say to yourself, how come there is a predetermined standardized number that will not change? That is the chance of committing an error. So if someone brings erroneous data, very bad, he created it himself, he faked it, then the chance of him committing that error is similar to mine? What the hell? It's not. So alpha is the standardized cutoff that we utilize to see if to accept or reject our alternative hypothesis. Wait with me. And usually the value of alpha is 0.05. So there is a 5% chance of committing a false positive, saying that alternative hypothesis is true while it's not. So alpha represents the chance of you saying that alternative hypothesis is true, there is an association, even though in real life there isn't. Now, it's 5% the cutoff. If your p-value happens to be less than 5%, less than 0.05, then you confidently say, I'm below that cutoff. I will claim in my study and I will write it down that there is a significant association. That there is an association. I can claim that the chance is less than 5%, less than alpha. My p-value is less than alpha. You claim it. However, if your p-value, for example, turned out from your statistical test to be 0.07, that's 7%. It's more than 5%. You claim that there is no association. So that's from where how they interpret the p-value, and also why alpha is fixed. So alpha is fixed. What differs from one data to another, from one statistical test to another, is the p-value. And we judge it based on our predetermined alpha. So it became very famous in research that we will accept an alpha of 5%. Now, your p-value happens to be more than that. There is an 8% chance that you say there is an association while it's not. This is a high risk. We are not going to trust you. Then report that there is no association. You are less than 5%. Your p-value is less than alpha in your test. Again, every test returns this p-value, the relationship between two variables. It's less than alpha, less than 0.05, then okay, we trust you. Report that it's significant. All right? If p-value equals 0.05, then it equals alpha, and this means there is a 5% chance. And that's usually insignificant, meaning that there is no association. So it has to be less than 0.05, just for people wondering if it was exactly 0.05. Now, if you see from the way I'm talking, the only difference between alpha and p-value, alpha is predetermined cutoff, while p-value is something that depends on your data and the test you have performed. So we can conclude that they are really similar, right? One of them is predetermined cutoff, and one of them is differing from one study to another and from one data set to another. So what does p-value? What's the definition of p-value? So let's say it's 0.03 in my study. It's below 0.05. It's a 3% below 5%. We are going to interpret it as significant, and there is a difference. However, someone comes to me and asks me, Asim, tell me, 0.03, 3%. 3% what? It's the same. It's a 3% chance that I said that there is a significant difference. However, in real life, there isn't. It's literally a 3% chance of committing a false positive error. So you can see how p-value is literally the same as alpha. Alpha is fixed, p-value is different from one test and data, and we judge it based on, is it more or less than alpha? I hope you got my point. I hope, okay? Usually I get feedback during my sessions. Now I'm not sure. Are people understanding me? Please comment out if you did understand. Okay, so let's solve these questions. A large study of serum folic acid levels in women aged 16 to 45 reveals that serum folate is normally distributed with a mean of 5 and a standard deviation of 0.5. Based on the study findings, 95% of serum folic acid levels fall within the following ranges. So this is a question back to the normal distribution. I want you to solve it on your own. I'm not going to answer it. Now this question is based on the hypothesis testing. What does this p-value imply about the null and the alternative hypothesis? A clinical trial is conducted to compare the effectiveness of two different antibiotics for treating pneumonia. The null hypothesis, which claims there is no difference or no association, says that there is no difference in the effectiveness between the two antibiotics. So for example, we were comparing cephalexin and ceftriaxone. The null hypothesis, there is no difference. The alternative says there is a difference. It says ceftriaxone is superior. After performing our analysis, it turned out that the p-value is 0.01, which is statistically significant because it's below the alpha value of 0.05. However, what does 0.01 mean? It means that, what does it mean? That's not the question here, but what does it mean? I want you to tell me. It means that there is a 1% chance that I'm going to say that there is a difference, but actually there wasn't. So, what does this p-value imply? Since it's 0.01, it's less than 0.05. Is the null hypothesis proven true? Is it rejected in favor of the alternative? Is the alternative true? Is the null accepted? Or the null is inconclusive and we can't make a decision? Obviously, we have explained it. So if it's below 0.05, you will accept the alternative and say that there is an association while rejecting the null. So it's B. You will reject the null and you will say that there is a difference. So the answer is B. Now, a researcher is conducting a study to determine whether a new drug is more effective than the current standard treatment for hypertension. They perform a hypothesis test and obtain a p-value of 0.03. What's the correct interpretation of this p-value? I hope you can answer this on your own. It will be B, that there is a 3% chance that the null hypothesis is true. So he said that there is a significant difference. This p-value was 0.03. It's below the alpha of 0.05. So he can claim that there is a significant difference, but nevertheless, nobody is 100% certain. There is a 3% chance that he might have committed a false positive error, type 1. Now, a pharmaceutical company is testing a new drug to see if it lowers blood pressure compared to a placebo. The null hypothesis states that the drug has no effect on blood pressure. So again, the null hypothesis, there is no effect, there is no association. That's what it always claims. While the alternative claims that the drug lowers blood pressure. After conducting the study, the researchers mistakenly conclude that the drug is effective. So they said it's effective, although it's not, even though it actually has no real effect. So what's the error here? They said there is an effect, so that's the positive. However, they were mistaken, so it's false positive type 1 error A. All right? So that was hypothesis testing. Now I'm going to move to the topic of sensitivity, specificity, positive predictive value, and negative predictive value. And we will conclude that video with this topic. However, it will take some time, so I'll take a minor break and continue recording and have a sip of my coffee. Have a sip of yours also. Hello everyone, back again to the topic of sensitivity, specificity, positive predictive value, and negative predictive value. And I know this is a nightmare. Too many individuals. However, I promise you, focus with me and you will finish this video liking me, I really hope. So, first of all, what I want you to never forget, in the 4 of these equations, the truth is always the numerator. The truth is always above. The truth always rises, right? Didn't Batman say that in one of his movies? So the truth is always the numerator. Look here, true positive. Look here, true negative. Look here, true positive. Look here, true negative. So that makes it easier. Now, and that's only for the equations. I don't want you, it will help you in the questions, but like don't fixate, all right? Focus, don't fixate. Sensitivity and specificity, your denominator is based on the disease status of the patient. While in the predictive values, it's based on the test result. So, sensitivity, again, the truth will be above. And literally everyone within this equation have the disease. Here, everyone within this equation in specificity doesn't have the disease. So really it's based on disease status. So in sensitivity, truth is always above. So true positive divided by the combination of a true positive and false negative. True positive means the test is positive and it's true, he has the disease. While false negative, the test is negative, but he has the disease. That's why we call it a false negative. So literally everyone in this equation has the disease. So specificity, the absolute opposite. Again, truth is going to be the numerator, so true negative divided by true negative plus false positive. True negative is someone whose test is negative, and yeah, true negative, they don't have the disease. And false positive is someone whose test is positive, but that's false. They don't have the disease. So everyone in this equation of specificity doesn't have the disease. Everyone in the equation of sensitivity does have the disease. In positive predictive value, everyone has a positive test. And again, the numerator is the truth. So true positive on true positive plus false positive, because everyone is positive here. Negative predictive value, everyone has a negative test. So true negative on true negative plus false negative. The shared thing between people in predictive value is the result of the test being positive or negative. While in sensitivity, it's that all of them have the disease. In specificity, is that all of them do not have the disease. And then in all of these equations, your numerator is a single number that's true, and you can easily figure it out. When you are in sensitivity and we mentioned that all of them have the disease, is it going to be the true negative or the true positive? Obviously the true positive. In specificity, counterwise, it will be the true negative. And positive predictive value, it's people with a positive test. And again, the numerator must be true, so true positive, and so on. I will repeat the statement just once for people who didn't understand. In sensitivity and specificity, everyone within these equations is classified based on their disease status. If we're talking sensitivity, the whole equation is individuals with the disease, truly with the disease. And in specificity, it's people without the disease. In predictive values, it's based on the test. Positive predictive value, all of them have a positive test. Negative predictive value, all of them have a negative test. So this makes it easier to understand the equations. Now something else, sensitivity is good to rule out or rule in. They examine this concept, which is really good to understand. It's good to rule out. Why though? Why? Look at the ratio. Look at the ratio here. It's the true positive. So if the test is positive, I have the disease over every individual with the disease. So if that test was high sensitivity, you mean that true positive over true positive plus false negative is almost 1 or 100%. Meaning that false negative is really very minimal, right? For this ratio to be high, it's like dividing true positive over true positive, because you want to minimize false negative. Because that's how it will be, because this is the population of individuals with the disease. So the more of them is true positive, the less of them is false negative. That's how you imagine the population of people with the disease. So if the test is that good, that means it's sensitive. So if someone is not positive for the test, it's very unlikely they have the disease. An example of that is D-dimer. When we have a low-risk pulmonary embolism patient, we order a D-dimer, and if it's negative, you don't do a CT pulmonary angiogram, you don't investigate, you don't treat. Why? Because you have ruled it out. It's a high sensitivity test. Everyone with pulmonary embolism, meaning every true positive and false negative, everyone with pulmonary embolism, it's very likely, high sensitivity test, it's very likely among these all people that they will be true positive. It's very rare that someone with pulmonary embolism is a false negative, where the test will not detect him, but he turned out to have pulmonary embolism. That's very rare. So it's very good in ruling out. However, is it good at ruling in? Sensitivity doesn't determine that. What determines the goodness in ruling in is specificity. Is the dimer specific? Infections will increase it. Other thrombotic events other than pulmonary embolism might increase it. Pregnancy, a malignancy that's hidden. I mean, there is hematologic causes. So sometimes you don't know the cause, it's just arised. And that's why in the algorithm for pulmonary embolism, if your D-dimer is positive, you don't go on and give empiric anticoagulation or thrombolysis or mechanical thrombectomy or an invasive step. You go on and do a CT pulmonary angiogram, because that study is specific. It will show you the pulmonary embolism. And by the way, it's both sensitive and specific. There's tests that have both features, and imaging usually, especially in visuals, have high sensitivity and high specificity at the same time. However, the reason in the algorithm you go for D-dimer first, it's less radiation, there is no contrast, and it costs less. So it makes sense from different points. So back to our topic. So after your sensitive, only sensitive, it's not specific test, is positive, you go and do the more specific testing. And in this case, it's the CT pulmonary angiogram. And why do we do the CT pulmonary angiogram? Because if it says, if the radiologist tells you we didn't see any pulmonary embolism in that image, he's very likely to be true. So when he says it's negative, when he says there is nothing, the ratio between saying that there is nothing and actually that there is nothing, so true negative plus false positive, like among all the negatives, when it's true negative, among all people without the disease, it's very, like, among the people without the disease, you will not find the pulmonary embolism. If you bring someone from the street and you do a D-dimer, it might be elevated. If you do a CTPA, you will not find the pulmonary embolism. So it's a very specific test. It rules in. Once you see the embolism, it's there. All right? So sensitivity rules out, specificity rules in. That's a concept I want you to know. Now, I'm going to move to questions. I hope that the equations are now easier for you, the equations, and also that you understand that sensitivity rules out, and the D-dimer example is a very good one to remember, and specificity rules in. All right? So let's go for the first one here. And these questions are really important because they use these sentence phrases where it becomes kind of an English test, where you need to understand that a patient, for example, comes with a positive ELISA for HIV, and they want to ask you, given that my test is positive, what's the chance that I actually have HIV? Like, my test is positive, what's the actual chance I have HIV? And that's literally the question here. So the patient asks, what are the chances that I actually have HIV, given that my test result was positive? So what metric answers his question? Don't rush it. When the statement that they give you, the question that the patient asks, mentions the result of the test, it says the test is positive, the test is negative, he is referring for a predictive value. He said the test is positive, that's the positive predictive value. He said it's negative, that's the negative predictive value. Why? Because if you turn his question into an equation, he basically says, what are the chances that I actually have HIV, given that my test is positive? So I have HIV and the test is positive, that's a true positive. So my numerator is the true positive. Just by knowing that, I cancel negative predictive value and specificity. Then what's my denominator? If given my test is positive. So it makes no sense for the denominator to include people with a negative test. If you look at the equation for sensitivity, the denominator is true positive plus false negative. While for positive predictive value, it's true positive plus false positive. So really, this is the equation that answers his question. Among people with positive tests like me, what's the chance that I actually have it? So true positive over true positive plus false positive, positive predictive value. Now let's calculate it based on this table. True positive is when the test is positive and the disease is there, so 90 over 90 true positive plus false positive, which is the positive test that's false, so 10. So 90 over 90 plus 10 means 90 over 100, so 90%. The answer is D. All right? Now, obviously, again, talking, so pause me. You can do that. It's a nice feature in YouTube. Please do it and solve these questions on your own after I explain them. So once again, when I solve them, you get to understand your weaknesses. This is really vital. I don't want you just to watch me. I want you to solve these questions. A different patient gets tested using ELISA for HIV, and his result comes back negative. He asks, what are the chances that I really don't have HIV, given that my test was negative? Again, what are the chances I don't have HIV while I'm negative? So what is he looking forward for? What he's trying to say? My test is negative. Okay, I was really worried that I would have HIV. My test is negative. However, how much can I trust it? Like, what's the chance that I'm really, really negative? So what he's asking for is true negative, where his test is negative and he really doesn't have the disease. So true negative is my numerator. I have cancelled out sensitivity and positive predictive value because their numerator is true positive. Now what's the denominator here? Again, he says given the test is negative. It makes no sense to have a positive in your denominator. So it will be true negative plus false negative. So among the people with a negative test, how many of them are actually true negative? That's what he is asking. So true negative over true negative plus false negative, What is that? It's the negative predictive value. How to calculate the true negative is a negative test with a negative status, so 90 over true negative again plus a false negative. So 90 plus 10, 100. So 90 over 100, 90% again. Okay? Now, a researcher is evaluating the effectiveness of the ELISA test for detecting HIV, and he asks, how well does this test identify patients who actually have HIV? As you can see in his question, he didn't state the status of the test being positive or negative. He said, how good is it at identifying people with HIV? The only thing he mentioned is people with HIV. People with HIV is everyone with the disease. How good is the test as in identifying people from this disease population? So say I bring 100 people. In my lab, I did a PCR, they have HIV. Let your test now, how many people will it detect from these people? Proven HIV, but I want to see your test being positive. Basically, he's asking about the sensitivity. So true positive over true positive plus false negative, because your whole equation is going to include people with the disease actually have HIV. So sensitivity, calculate based on this table, true positive over true positive plus false negative. So true positive is 90 over 90 plus 10, which is the false negative, 90% again. Someone else asks, how well does this test avoid falsely identifying someone as HIV positive? Now, don't mistake this positive to the positive predictive value. He doesn't say that the test is positive. He says, how well does this test avoid falsely identifying someone as HIV positive, like labeling them as people with the disease? So, and he mentioned falsely here, so if you apply some math and try to reverse this question, which I really know is silly, but basically it's the reverse of this one. Basically he is saying, how well does this test identify negative people without the disease? However, we reversed it. We said it avoids falsely identifying people with, like, as HIV positive. So basically this is specificity, and it's the true negative over true negative plus false positive. These can be difficult to keep in mind, so you need to memorize as well. So there is questions where they will bring you a test and mention that its specificity is 80%, and it will be a theoretical question. There will be very long lines in your choices, and they will ask you, what does that mean? It will mean that 80% of the time this test will avoid falsely identifying someone as with the disease. So you need to understand these theoretical sentences that reflect these biostatistic parameters to answer well in the exam. All right? Measurement, again, you do it for specificity. I'm not going to do it. Pause the video and do it on your own. Now, a laboratory director is considering lowering the cutoff for the ELISA test for HIV. How would this change affect the following test characteristics? Very nice question. Now let's say that in ELISA you have a 50, like a 50, whatever it is, like, I don't know, usually there is like a reactivity. So let's say this reactivity is measured by the amount of light emitted, and they measure the speed of that light. Let's make it stupid, and the cutoff is 50. If your speed is more than 50, that's a positive test. Less than 50, it's a negative test. All right? Now, this researcher or laboratory director says, what is 50, man? I want to make it 40. He wants to lower the cutoff of the test. This means, if he moves it from 50 to 40, this means that people previously, before today, who got 45, they were regarded as negative test. From today's on, they will be positive test. And everyone in that range, between 40 to 50, is now becoming positive before they were negative. So he is playing with the balance, because now I will see maybe more true positives, maybe more false positives, because he increased the amount of positive people, and he is also reducing the true negative and the false negative by doing that. So how does that affect these measurements? Because all of them include in their equations these numbers, like the true positive, the true negative. It's as if I have 1,000 people and I tested them with the 50 cutoff. Obviously, if you move it to 40 over the same 1,000 people, your true positive, true negative, the number of people in these categories is going to shift. So how does that impact these parameters? Now, I will make it easy by understanding the equations, but also looking at, obviously this is an example you could use if you want, and measure the sensitivity, specificity, and the predictive values. However, I'm going to teach you this concept here, and then we will answer it in the question. So when you lower the cutoff, this means you will bring more positive individuals, because again, everyone above the cutoff is a positive. So if you make it 40 instead of 50, people who are here between 50 and 40 will become positive. This means you will increase the false positive population and the true positive population, while reducing true negative and false negative. How will this impact equations? Basically, I hope that I made it clear. When you reduce the cutoff, the positives are increased, true and false, and the negatives are reduced, true and false. How will this impact the equations? Look at sensitivity. Your numerator is the true positive that will increase because you lowered the cutoff. Definitely you will detect people who were not detected earlier. True positive will increase. False negative, what will happen to it? You tell me. Again, the negatives will decrease. So you tell me this increases, and this decreases. So what will happen to sensitivity? It will go up. It will go up. If you increase true positivity by 5, numerator is up 5. Here it's up 5, but then this is down 5 or 4 or 3. So you increased 5 here, you increased 3 here in the net. So the ratio increased, so sensitivity increased. So when you lower the cutoff, sensitivity increases. How about specificity? True negative is less because all the negative is less. True negative is less, and false positive is up because we lowered the cutoff. There will be true positives and false positives. So this is down 5, this is down 5, but this is up 2. So this is minus 5 over minus 3. The reduction in the numerator is more than the denominator, so specificity will go down. So lowering the cutoff reduces specificity, increases sensitivity. That's what we have learned about it so far. How about positive predictive value? When you lower the cutoff, again, the positives increase. So true positive increased by 5, true positive increased by 5, but false positive, let's say, increased by 2, because all the positives will increase. So 5 over 5 plus 2, that's 5 over 7. So actually it is reduced, because here you have 2 positives, here you have 1. So positive predictive value is reduced when you lower the cutoff. Here it's the opposite. True negative, again, all the negatives will be reduced. However, here you reduce 5, you reduce it here as well, along with some reduction from the false negative. So the denominator is reduced more than the numerator. So here it's, for example, minus 10, here it's minus 5. The reduction is more here. This is reduction, so the negative predictive value goes up. So if this was 50, now it's 40. And if this was 20, now it's 15. So if you calculate the ratio, it will increase. That's the whole concept. So sensitivity and negative predictive value increase if you lower the cutoff, and specificity and positive predictive value decrease. If you increase the cutoff, which is the right shift, so he decided instead of 50 he will make it 60, you will reduce sensitivity and negative predictive value, and you will increase specificity and positive predictive value. I hope you did understand it based on the equations. If you didn't, memorize. You lower the cutoff, sensitivity and negative predictive value increase, specificity and the positive go down. You increase the cutoff, it's vice versa. All right? And there is this statement, which again we will be just asked about it theoretically without an explanation, so let's not waste time on it. Whenever the prevalence of a disease in a population increases, positive predictive value goes up, negative predictive value goes down. Just memorize that. It has nothing to do with this plot and the cutoffs. Just know it. All right? So whenever a disease is commoner, positive predictive value is higher, negative predictive value is lower. Now back to our question. It was saying that he wants to lower the cutoff. Now we understand that lowering the cutoff will increase sensitivity and negative predictive value while reducing the positive predictive value and the specificity. So the correct answer, increase, decrease, decrease, increase, it's A. All right? I hope that the video was helpful. I think it covers a very good proportion of what you expect to see in your exams, not just USMLEs actually, because biostatistics and these concepts are universal. You expect them in every clinical examination that you will encounter post-graduation. So I hope that it's helpful, and I will be sharing with you the complete videos very soon. I will put it on the website for a very affordable price, and I really care that you guys really learn. So please, please, please leave in the comments any questions you have. I really love explaining biostats. It's one of my favorite topics. So I will be more than happy to help in the comment section. Thank you for watching and see you in the next one. Bye bye. Coffee. Bye bye.